All right, today we're going to introduce what I call phase 3 of our projectile motion. We have talked so far about objects in free fall, where they are moving along the vertical axis only. At first, we talked about objects that start at some position above the ground and then simply fall straight down to the ground. Then we talked about objects who started at some position. It could be on the ground, could not, but then the object was given a velocity that sends it upward. The object at some point is going to slow down to the point that it stops, and then because of the effect due to gravity, it's going to begin falling so that it is now going back down towards the ground. And so I like to call this up-down free fall, but these are both types of free fall where we are only moving along the vertical axis and the only effect is gravity. So today we're going to talk about phase 3, which is a projectile that starts some position above the ground, but now this object is given some sort of forward or horizontal velocity. And so because of gravity pulling it down to the ground and the velocity it was given sending it forward, the object is now going to follow something like this little dotted line here, which gives it a curved or arch-shaped path as it falls. So if we were to complete this diagram or make it symmetrical, then it would make a parabola, right? So we say that these projectiles follow parabolic motion because it makes or mimics the shape of a parabola. So projectiles, remember, are any of our objects that are moving through the air affected by gravity. So if we throw a ball straight up on a line, that is not parabolic, but if we toss it so that it moves both horizontally and vertically, then we are going to see that curved parabolic shape. A ball that rolls off the table, now just to clarify, rolling on the table obviously is not a projectile. The moment it rolls off the edge of the table where it is now moving through the air affected by gravity. So that, if you can picture a ball rolling off a table, you can probably begin to visualize that forward and downward motion. So now we must consider both vertical and horizontal motion. And I like to take it a little bit further and say we actually must not only consider vertical and horizontal motion, but we have to clearly identify that our variables are in the vertical direction or along the y-axis, or the variable is in the horizontal direction or along the x-axis. So we now can either put subscripts of x and y. If you'd prefer, you can put h and v for vertical and horizontal, but we need to clearly identify it. When I do my math work for this, I actually prefer to create a data table where I can put all of my horizontal givens on one side of the chart, and then I put all of my vertical givens on the other, and it helps me to keep everything clearly organized and labeled. It also helps me to keep track of what numbers are allowed to go into my math problems. So we'll see what that looks like a little bit later when I do a practice problem. So if we look at this page, this is intended to just kind of introduce how we come up with that parabolic shape. It says here that the first picture, they wanted us to draw the position of the dropped ball at 1 second intervals. So if my object starts here, and I've already done the math, so I'm just going to tell you how this goes. After 1 second, we would be on the 1 centimeter mark. After 2 seconds, we'd be on the 4. After 3, we'd be on the 9. And after 4 seconds, it would finally hit the ground here at 16 centimeters. The picture on the right is showing us a situation where there is no gravity. Now, if we were in far outer space, far enough away to be outside of Earth's gravitational pull, we could actually throw a ball like this, and it would follow a perfectly straight horizontal path because there are no forces there acting on it. Well, that may not be the case on Earth. We do have forces acting on it, but if we look at all of our forces in the horizontal direction, we are asking you guys to ignore air resistance. So if we don't have air resistance, even here on Earth, this is the horizontal path, or I should say this path shows the horizontal motion that the object would actually experience, even here on Earth. So what we can see from the illustration is that horizontally speaking, we have a constant velocity. We can see that each of these dots are equally distant, so that means it covers the same distance for every 1 second of time, so our velocity is constant. So what we're going to do now is we're going to take these two pictures and we're going to put them together so that it shows us where our ball would be located at each of these moments. So if I were to take my horizontal displacement after 1 second, my vertical displacement after 1 second, and combine them, then in real life, this is where my object would be located after 1 second of time. It has moving forward, and gravity working only on the vertical axis has caused it to fall at the same time. After 2 seconds, we would see its new horizontal position. And then vertically speaking, because of the acceleration due to gravity, it has fallen even farther. And so here's what my object would be after 2 seconds of time. So if we were to show where our object is in real life, it's basically an X and Y coordinate system between our two pictures to create that real life path that, if we follow, makes that curved or parabolic path that we were talking about. Okay, so the last thing on the screen, how does the vertical motion affect horizontal motion? It doesn't. Vertical motion happens, horizontal motion happens. One does not affect the other. They simply both take place on the same object simultaneously. So we have horizontal motion that is constant, and we have vertical motion that is affected by gravity. But one does not determine the other. Again, whenever we do our math work, we're going to need to isolate what is horizontal and what is vertical, because one does not affect the other. We have to perform our calculations so that it's only along the correct axis. All right, on this slide right here, I really just want us to look at this picture. So we have a projectile that follows path 1 here. So here is the landing point of our first projectile. Here is the landing point of our second, and here's the landing point of our third. And obviously they are landing at different places. So what I want you to understand about this is, in order for these projectiles to reach different horizontal positions, they had to have different horizontal velocities. So the velocity in the X direction is what determines how far the object is going to land, okay? So that horizontal velocity determines the horizontal displacement for our projectiles. All right, horizontal velocity is constant, vertical velocity changes. Horizontal velocity is constant. It does not change. It's always the same value. Once we know what that number is, it's the same value all the time. Vertical velocity, remember, along the vertical axis we have gravity. Gravity is an acceleration, which means it's going to change the velocity. If the object is going up or down, affects how that velocity changes. But in general, we know that along the vertical axis, that velocity is going to vary. So that's why we have our VIs and our VFs when we're doing math on the vertical axis. All right, here are just some statements about projectiles, and I'm going to just kind of move this so we can focus on one at a time. So it says here, projectiles always maintain a constant horizontal velocity. So I put V in the X direction, which would be one way to notate horizontal velocity. And I put a blank in front of my meters per second because I don't know what that number is, but it has to be some number. It can't be 0, but it could be any other number. Okay, so we have to have a velocity horizontally. And then that velocity is constant. Here it says projectiles always experience a constant vertical acceleration of meters per second squared downward. So I wrote to the side A in the Y direction. So whenever we are doing calculations along the Y axis, we will always use negative 9.8 meters per second squared as our acceleration in those calculations. The next thing here says vertical and horizontal components are completely independent. And so that's what we discussed on the very first slide. For projectiles that go up and come back down. So it says for projectiles that begin and end at the same height. So this object went up and came back down. So the beginning and ending positions are the same vertical position, okay? There's two things we need to know in this particular situation. The first thing is that the time that it takes for the projectile to go up is the same amount of time that it takes to go down. So if you've worked some questions about projectiles that go up and come down, you may have noticed that some of the questions want to know how much time to the peak. Others want to know what the total time is. We might ask you for both. We might only ask for one. And so understanding that there is an up and a down phase, that both have to be accounted for. But if I know that my total time was 8 seconds, then how much time does it take to reach the top is only 4 seconds. So understanding that relationship is going to be very helpful with both conceptual, but more often with the mathematical calculations you'll need to perform. The speed of launch and the speed of landing is the same. So we've talked about this in a previous lesson, where the initial velocity upward could be 50 meters per second. If that projectile comes back to the same vertical position, so it goes up and comes back down to the same spot, to that launch height, then we would say that the velocity would be negative 50 meters per second. The magnitudes of those velocities, aka the speeds, are the same. Velocities are vectors, so if it's asking for a velocity, we must make that downward a negative, okay? And then this is a very specific situation here, but it says for a projectile that is dropped from a horizontally moving vehicle. So if I have an airplane and that airplane is carrying a package, and this package needs to be delivered by air. If this airplane is traveling with a velocity of 200 meters per second, well, that package is also traveling with a horizontal velocity of 200 meters per second. So if this airplane drops the package, that package is not going to fall straight down and land directly below the point where it was released. Because it is connected to our airplane, the velocity of the airplane serves as the velocity of my projectile, or of my package in this case. So if this package is released, it's going to move forward as it falls because it was given an initial horizontal velocity. All right, so now we're going to switch and do one practice problem. Oops, sorry, I opened the same document. Let's try that again. All right, so we're going to do one practice problem here, and I'm going to explain in very good detail how we are going to organize our information and give a couple of strategies for how you could organize this information when you're working on your own. So first we want to read the story. Throw a rock horizontally at 22 meters per second from a 315 meter tall building. How far from the base of the building will it land? Now, if I were to ask my students to list their givens without any kind of instruction, what I typically see is that students would just do this. And they may or may not also add that. Okay. Yes, these are variables and this is my unknown, but that information is not specific enough. This is too vague. Number one, why do I have two different values for D? Is the answer really 315? Is this one of those like tricky conceptual questions? It's not. We do have to do a calculation, but remember, now that we have both vertical and horizontal motion taking place, or motion along those two axes taking place, we have to clearly specify that this is a vertical or a horizontal velocity, a vertical or horizontal displacement. So what we're going to do now is we're going to read this again, but I'm going to draw a picture to go along with it. I really love the pictures. I feel like the pictures just help so much with organizing, comprehending, allowing your brain to focus in on what is happening at that moment or maybe at that location. And then there are a lot of facts that you're going to need to recall when working through these problems that are going to lead to knowledge for values that go in the math work that maybe aren't clearly stated in the question, but because of the situation, you should know some of the values that need to go in your problem. So we have a rock and it's being thrown horizontally from the top of a building. So first I'm going to draw my building, and then here I am, and I've got my rock, and I'm going to throw my rock forward. So if I'm imagining this in my mind, that rock is going to go forward and it's going to fall so that it lands over here somewhere. this is the situation. So now I'm going to say, well, they gave me a velocity of 22 meters per second. This is how fast the ball was moving forward when I threw it. So this specifically would be along the horizontal axis from a 315 meter tall building. So this height is 315 meters. How far from the base of the building? So if we were doing this at the school, we would take our meter stick and we would lay it down along the grass from the edge of the building to the location where it landed. So they are asking us to find our displacement along the x-axis, okay? So do you have to put your, well, first of all, do you have to draw a picture? No. Do you have to put the values on your picture? No, you do not. These are all just suggestions, just strategies that you might want to try in order to help you work through a problem or figure out what you're supposed to do with the values. What I'm going to do now is create a little table. I like to put my table in the middle of the paper because it basically helps me to divide my paper into two parts. And I personally like to put only horizontal information on the left-hand side, and I put only vertical information on the right-hand side. So it helps to just really organize, and as I continue working through my problems, it's also going to help to create patterns, and my mind, my eyes, my brain are going to start to recognize, hey, this is what we did in this situation in the past. And so I just really pick up on how to work these problems so much more quickly this way. I do not typically ask you guys to write your variables and then try to fill in all the spots, but because I am aware of the 4 different phases that we're going to be working in, and all of the different variables and situations we're going to have, I do actually recommend that we start off with a template. Okay, so this is my template that I'm going to use whenever I'm working through these problems that have both vertical and horizontal motion. So now I'm going to take the information that I'm given and I'm going to put it on my data table. So we are given a horizontal velocity of 22 meters per second, and it asks me, well, let me pause for a second. In the horizontal direction, we said that velocity was constant, which means that there is no acceleration. So always, always, always on the horizontal side, we're going to say acceleration is 0, or you can even just kind of scribble it out. There is none. So now they are asking us how far from the base of the building. So this is my unknown. Now, since velocity is constant, since there is 0 acceleration, V equals d over t is the formula that we want to use when we're dealing with horizontal motion, because no acceleration is needed. Notice I don't have a VI and a VF because velocity doesn't change. All right, so if this is my equation, then I could say 22 equals d over, I don't have a value for d or t. And since I've already established that these are the only variables on the horizontal side, now I have to go and I have to ask myself, well, how can I finish this math problem if I don't have time? And I can't use the variables on this side to find time because I don't have enough information, right? So it kind of turns into, what in the world am I supposed to do here? Well, the time that it takes for a projectile to fall vertically is the same as the time that it takes for a projectile to fall horizontally, and that's because while it's in the air, it is a projectile. So we have a quick little demonstration here. This guy is setting up a device that's going to drop a marble from one end at the same time that it's going to push a marble horizontally from the other end. So this lever is going to affect both of these objects at the same time, and you see this one, it goes perfectly horizontally, just like what we're discussing. So now he's going to go ahead and he's going to set up the machine. He's going to put both of the objects on the machine, and then when he releases the lever, you'll see that they both fly at the same time, and they both land at exactly the same time. And so what we take away from that is the knowledge that the amount of time that an object spends in the air, specifically the total time that the object is moving horizontally, is the same as the total time that the object is moving vertically. So although I said that this is going to serve as a boundary, a barrier between my right and left side, my vertical and my horizontal, all walls really should have doors because nobody wants to be trapped inside of four walls, right? So what we're going to say is that time is our doorway that allows us to move between vertical and horizontal motion. Because the total time that the projectile spins in the air is the same for both vertical and horizontal motion, the total time will be the same value on both sides. So now I'm going to come over here to the vertical side of my data table, and I'm going to see if I have enough information to calculate time using vertical motion. In the problem, they gave me a height of 315. Remember, this is a displacement, so we're going to list that as a negative 315. It is starting at the absolute highest vertical position. So along the y-axis, remember the velocity at the highest point is 0. So in this case, it is going to serve as my initial velocity because it started from the highest point. In the vertical direction, we always have our acceleration due to gravity. So my acceleration is negative 9.8 meters per second squared. So now that I have all of my variables, I'm going to go to my list of I'm going to go to my list of equations. I'm looking for time. I have d, vi, and a. And so that leads me to d equals vit plus 1/2 at squared. So when I go to substitute my numbers, remember vi is 0, so all of this becomes 0. So I'm going to just choose to simplify this to negative 315 equals 1/2 of negative 9.8 times t squared. Half of negative 9.8 is 4.9, so I'm going to divide both sides by negative 4.9. So this cancels out, and that gives me, sorry, I thought I had my cheat sheet handy so I could write that down for you real quick. Let me find what that gives me. That gives me there we go. 64.285. And there are more digits in my calculator, so I'll just put dot, dot, dot. Now that equals t squared, so the last thing I'm going to do is square root, and that is going to give me 8.0178, and then once again, more digits in my calculator. Now please pay close attention here. We are not going to round this. We're not going to box it in. We're not going to do sig figs or units because the question did not ask me to solve for time. Look at my data table. My question mark is for the horizontal displacement. So now I'm going to take this 8.017, and that's going to serve as my vertical time, which is also the same horizontal total time. So now I can come over here to my original formula, and I can substitute in 8.017 dot, dot, dot. Now, when you do this in your calculators, please use that answer button, okay? So we want to make sure that we're getting all of these decimals accounted for. So I'm going to multiply both sides by 8 in order to get d all by itself. And now that is going to give me 176.39. This is what I'm solving for. This is the value I want to round for sig figs. My least number of significant figures was 2, so this is going to round to 180 meters. All right, I'm going to do one more example problem with you. This one, I'm going to go through a little bit quicker because I've already explained the process of how to use the chart. So let's look at question number 3. It says a baseball pitcher throws a ball at 40 meters per second towards home plate. The ball is thrown horizontally. how far will it drop on its way to home plate, which is 18 meters away. Okay, so for my visual people, here is the pitcher. He's got the ball. He's going to throw it to home plate. They told me how fast he threw it. They told me how far away home plate was. And so that is the picture of what I am working with. So let me make my little chart, cut my page in half, and let's start listing our variables. Okay, so in the horizontal direction, they gave me the horizontal velocity. He threw it 40 meters per second. They gave me, the horizontal displacement of 18 meters. Sweet. My acceleration is 0 because it's horizontal, so there is no acceleration. So is it asking me for time? No, it's not asking me for time. It's asking me how far will it drop. So this makes it along the y-axis. So over here, I'm going to list these same variables, but they are asking for this displacement. That's what they want to know, okay? So now we are going to say, well, along the vertical direction, I know I have gravity. And they don't really give me any vertical information in the written problem. But once again, if I look at my illustration, this object starts at the highest possible vertical position. That velocity is forward, it's not upward. So in the vertical axis, as far as up and down goes, from this moment, gravity begins pulling it downward. And so its initial velocity is 0 at the highest point, and then it moves downward. So my VI is a velocity of 0, okay? So I need to find my vertical displacement. So VIT plus 1/2 AT squared is going to be my best bet. If I went through the list of all of my equations, I actually would have found in this case that I don't have all of the parts to any of them. So here's where it's really important that you are following the process. If you ever get to the point where you cannot use any of the equations because you are missing information from all of them, ask yourself 2 things. Question number 1, is there a number? Is there a number I should know? In other words, did you maybe forget that the initial velocity was 0 in this situation? Did you forget that acceleration was 0 because it was a horizontal question? Did you forget that the acceleration was negative 9.8 because you're analyzing the vertical axis? Is there some number that I'm just supposed to know? Okay, that's the first question. If the answer to that is no, then you go to your second question. Is there a number that I can solve for? And so in this case, there were no equations where all of the information fit, but if I could find my time, then I could have enough information to use d equals VIT plus 1/2 AT squared to solve the problem. So then I need to start thinking, can I find time? How can I find time? But I don't have time. But remember, the total time is the same for both of my axes, both vertical and horizontal motion. So if I come over here to the horizontal side, remember, we know this is V equals D over T. I have my V, I have my D. Yes, I could solve for my time, which would give me my horizontal time, which becomes my vertical time. So that's what we want to do in this case. All right, I want to take a moment and I want to review how we solve for T. We still have some students that are struggling with this. So whenever your unknown is in the denominator, remember we're going to multiply both sides by that value so that it gets my unknown as a whole number instead of a fraction. So I have 40 times T equals 18. And then now I divide both sides by 40. And so that is going to give me T equals 0.45 seconds. It came out to a perfect 45 in this case. So that number becomes my time here. So then this becomes my time here. And so now I have enough information to substitute and solve for my vertical displacement. VI is 0, so that is going to simplify to nothing. So 1/2 of negative 9.8 times 0.45 squared. Remember, please get in the habit of using your answer button. Even though it's a perfect 0.45, let's just practice taking the answer squared in our continued calculations. And so this gives us a value of negative 0.99225, blah, blah, blah. We are going to round this for sig figs. So let's look at our original measured values from the problem. And so we see that we had 40.0 as our first measured value and 18.0. Both of those have 3 sig figs. Leading zeros are not significant. So 1, 2, 3 significant figures. So I am going to write negative 0.992. Remember, this 2 stays the same. It has to be followed by a 5 or more in order to bump up to a 3. And then our unit here is meters.